Hello, everyone. This is Craig and Berge Design Day. This is project 21048, Visual Natural Language Processing of Medical Images for Enhanced Value. Our sponsor is the Center of Accelerated Biomedical Innovation, and our team consists of myself, Madeline Brown, Sean Brown, Sandoz Kolab, Andrew Muscola, and Ko Trurong.
So if you guys take a look right here, this is the poster that we've created to help aid in our presentation and discussion of the Q&A questions of our project. We're going to get into the introduction, the methods, the results, and ultimately the conclusions of what we actually did here in the rest of our Design Today presentation. So for now, we're going to go ahead and skip over this and move on with the rest of our presentation.
Hey, the table of content. First, I will talk about the introduction, then Shaw will work on the objective, and next, Madeline will introduce the approach to the problem and functional and system requirement. And after that, Sandoz will introduce the concept and design, and finally, Andrew will talk about the requirement, verification, and result. For the introduction, platelet activation, or PA, is central in thrombosis, which continue to limit cardiovascular therapeutics devices. Understanding mechanism of a PA and the time course and natural history of PA are vital in efforts to modulate thrombosis. The team has proposed a solution in terms of the analysis of platelets, and which a computer program will be developed based on the initial rationalized software of the Berge Design team from 2019 to 2020, and we will process, classify, and extract specific feature data on different steps of activated platelets.
Yeah, as Ko was saying, the software we're working on developing is to aid in the classification of platelet images and being able to extract the appropriate feature data from samples. Right now, commercial technology in the industry doesn't exist for the purposes of auto-classifying platelets and their different levels of activation. And that's what we seek to address with this software. So currently, as images are classified by a clinician, what happens is it takes up a lot of time, a lot of effort, and a lot of energy. And so we're trying to remove that with the introduction of the fractalized software, and we have achieved that.
Sweet. Now for our approach. The solution is an open source Python-based image analysis tool and neural network-based classification that will process and collect the valuable data needed for further analysis of platelet and platelet activation. The system as a whole will be able to take a user-selected image, user-entered grid size in terms of rows and columns, and a user selection of which voxels to process in order to classify/detect activated or resting platelets and extract the specific features from the image voxels. The features that can be extracted with our software include our centroid area, perimeter, major axis length, minor axis length, shape intensity, region average pixel intensity value, the minimum pixel value, maximum pixel value, perimeter/area ratio, aspect ratio, and shading. The user may also choose to extract voxel-wide average values, include averaging area, perimeter, and all the ones I said earlier. And all of this will be controlled by the user through the GUI interface. Now for our system requirements. These are just a total of what requirements we set back in the PDR. So obviously we have our interface requirements, our virtual system, which is our image pre-processing. We also have one for image classification, feature extraction, and some little ones such as patient data processing and storage requirements. The gist of these is that we need to be able to control the GUI. It needs to look nice and usable. We need to also be able to create these image voxels also be able to accurately classify the voxels, or specifically these platelets, be able to calculate all the data, display, and pretty much making sure that we're saving it all correctly.
In this slide, we see our system block diagram, and this system is broken up into four main subsystems. The CSCI software, which is the system as a whole. It will allow the user input and user selection of which image voxel to process in order to detect activated or inactivated platelets and extract specific features from the image. The features to be extracted are listed in the feature extraction. The GUI subsystem will be the start and finish point of the software operation. The GUI is designed to ask the user to select an image using the computer system default dialog by allowing the user to determine the rows and columns to divide the image into voxels and select features to calculate the feature extraction subsystem, and then select a directory to save the data generated after the subsystem is completed.
So verifying our system, we were able to pass each requirement except the accuracy requirement for image classification. The system is able to efficiently extract, analyze, and pass data to each system, although we were only able to achieve 70% accuracy rather than required 75% accuracy for the image classification I mentioned earlier. And this is an example of what our system is able to achieve. An image can be imported, then thresholded, where the white regions will represent platelets, and data such as the area, perimeter, and pixel values, which Madeline mentioned earlier, can be extracted from the regions and analyzed as region data, or the user can view the voxel-wide average data.
Great. Now for a demo and some conclusions that we were able to make from the data. Now to start off with some conclusions, here I have 4 different plots of resting and activated platelets at different levels of magnification. And here I actually have 4 different features that our design is able to calculate, which is area, perimeter, eccentricity, and shading. Now these 4 graphs actually prove our design does work, as you can see a distinguishable difference between activated and resting platelets, which is the main goal. Now we have another method to determine activation other than visually identifying it. Now for our demo. Starting off, we'll import an image, select our grid size and our voxel shape, select our features to be extracted, select our save location, import any patient data as a .text, and press that fractalize and extract button, which will pop up a window asking if you want to process all voxels or one. Once we get to the output window, we have our table indicating which voxel has activated platelets and what stages. And then we also be able to see each individual feature selected with all the data for each voxel, which is currently the average. And then we also have the .csvs for later access.